All right, so hopefully that was, a bit of it. There was a nice problem to really chew on here. What I really wanted to focus on was the logic that we used in the middle here with this. If Mike is a toad, we saw that if Mike was a toad, we ended up with things that didn't make sense. We ended up with a conclusion that went against an established fact in a problem here. And that is actually that's going to be a technique that mathematicians have a tendency to use. So if you look at the past 2 sessions we've been working here, we've been looking at what are known as direct logic proofs. Basically, the idea is you're given a bunch of things here, you're given a bunch of statements, so, something like what we did previously, something like this here. We're given a bunch of statements, and we get to our goal, and notice we do that directly. It goes directly there. Right? We show that this has to be true given the information that's given. However, notice here in this situation, we're making use of the fact that there is a contradiction here. And if there's a contradiction, that means we went down the wrong path. Okay? So in this situation here with something like this, we assume something here, and we said if Mike was indeed a toad, and we saw that there was something horrible that happened here. There was some sort of contradictory statements that are happening here. This method here we refer to as what is known as the indirect proof, or what we call the proof by contradiction. And I have, and I have the thing we have down there, so you can get the definition down. So we call this a proof by contradiction. It's a proof in which instead of showing a conclusion directly, we're going to assume the opposite of the conclusion, and we're going to force a contradiction here. Okay? So in general, the contradiction is basically mathematics' way of telling you, you screwed up, you have an error here. But the idea behind a proof by contradiction is that since we've developed this mathematical system, and this system is basically, this is basically underlying truth here, the fact that we end up with a contradiction means something went horribly wrong, and the only place that went wrong was at the very beginning. And we'll talk about how that works here in a bit, okay? So, with that in mind, let's take a look at a classic example here. So what we're going to do is we're now going to look at a classic example of the proof by contradiction. I wanted to focus on this example for multiple reasons. One, it shows that, first off, it's possible to look at proofs that are not purely logical based. And second, this really just shows the power of this proof by contradiction. So we're going to follow along here and look at this. Now, the key here is the square root of 2, this number square root of 2, which I think many of you are very familiar with. The square root of 2, as many of you know, is an irrational number. Now, we don't mean the fact that, it just babbles nonsense and just doesn't think. We mean the fact that it cannot be written as a fraction, a over b, where a and b are rational, or where a and b are integers here, right? And this is probably something you covered in middle school, the fact that the square root of a number that's not a perfect square is an irrational number. Now, certainly some of you have seen this before, certainly know that the square root of 2 is irrational. But I get the feeling that a lot of you didn't ask the most important question. Why? How do you know that? Right? So what we're going to do is I'm going to do a proof by contradiction to show you the square root of 2 has to be irrational. So I'd like you to follow along. We're going to fill in the proof here. So here we'll note we're going to use a proof by contradiction. So if you remember what we just said, a proof by contradiction here, we're going to fill it in. This proof by contradiction, we want to assume the opposite of the conclusion. Our conclusion is that square root of 2 is irrational. So we're going to assume the opposite of it. So therefore, we're going to assume that square root of 2 is rational. Right? This means that, so based on the definition of rational, square root of 2 is equal to a over b, where a and b here are integers. Now, we also want to make sure the fact that b is not 0. Right? Because if b is 0, then this explodes. We can't have a fraction with a denominator of 0 here. So a and b are integers and b is not 0. Now, the next part. Furthermore, let's assume that the fraction a over b is in lowest terms. That is, a and b share no common factors other than 1. Okay? So in this situation, we're going to assume this here, right? Because if you have a fraction, if you have any fraction, you can reduce it to lowest terms. Okay. So now it says, let's clear fractions and radicals by multiplying by b and squaring. So let's start with this here. Now we're going to do a little bit of algebra. So I'm going to multiply both sides by b. So then we get b radical 2 equals a. And now we're going to square both sides. I'm going to switch this order of the sides here. So actually, no, we'll leave it like this. Sorry. So we have b radical 2 when you square, you get b squared, and then you have a times square root of 2 is squared is just 2, is a squared. So therefore you get 2b squared equals a squared here, okay? So your algebra gets you to this part. All right. Now, we look at the left side of the equation. Wait a minute. So the left side of the equation, the most important thing on the left side of the equation is there's a 2. It's 2 times something. And notice that a and b are integers, so that means it's 2 times some sort of integer. Now, if you remember, a number that's 2 times an integer, that's even. So we know the left side of the equation is even. So the right side must be even as well, right? If this is even and these are equal, then this has to be even as well. So, wait a minute. Therefore, I now know that a squared is even, right? So we have 2b squared is even. That implies that a squared is even. So wait a minute. If you're multiplying by a number by itself and it's even, then there's only one possibility, and that original number is even. Thus, a must also be even, right? So this allows us to chain this into the fact that a is even. Okay? So now we can use the definition of even here. Right? We know what even means. Even means 2 times a number. So I can write that a is equal to 2 times some number k for some integer k. So I'm going to write a equals 2k. Now, I'm going to go ahead and simplify. I'm going to go ahead and substitute this back in. We have the fact that 2b squared equals a squared, right? Since we know a is 2k from what we had here, we're going to go ahead and substitute that in. Right? So that's that. So let's see. Let's go ahead and write this out here. So this is 2b squared equals, well, when you square this, you get 2 squared into k squared, so that's 4k squared, right? So now we have 2b squared equals 4k squared. We can divide both sides by 2 because there's a common factor of 2. We get b squared is 2k squared, right? Now this looks a lot like what we have here. That's good. Because now let's continue. Again, we look at the right side of the equation. The right side of the equation is 2 times an integer, so it's even, right? So 2k squared, this is even. Thus, this means that b squared is even. Thus, b is also even. So notice how in this situation we know b is even. But this is where the dramatic thing happens. This is the plot twist. This is where if this were a video game, this would be a major cutscene would show up here, all nicely hand-drawn cinematic here. There's indeed a contradiction here. Something has gone horribly wrong. So again, what I would suggest here is I'd like you to pause the video and read back through this and see if you can find a contradiction. Okay? Alrighty. So far everything looks pretty good, right? But there's something weird going on here. Notice we've concluded that a is even, right? This is an important piece of information. A is even. We've also concluded the fact that b is even. Wait a minute. So notice that we've concluded that a is even, b is even. There's a piece of information that we used up here that we never really gave much thought to, but it actually shows up to be very important here. Furthermore, let's assume that the fraction a over b is in lowest terms, as a and b share no common factors other than 1. So, let's look back here. A is even, and b is even, right? Thus, if we look at the fraction a over b is even divided by even. Since it's even divided by even, I can divide a 2 out of both of these things here. So, a over b is not in lowest terms, right? Because since we know that the numerator and denominator of these fractions both have a 2 in them, that means I can divide the 2 out, and we end up with, and I can get a fraction in even lower terms here. So a or b is not in lowest terms. But we were told that a and b is in lowest terms. So this is really, really important here. What we have just shown is we have this fraction a over b that has the property that it is in lowest terms and it's not in lowest terms simultaneously. This is horrible. You can't have that happen. That makes no sense, right? There's nothing. How is this possible? Notice, and this is the key about the proof by contradiction. This is a contradiction. You can't have something be not in lowest terms and be in lowest terms at the same time. Fine. Our logic, if you think about it, our logic here has been flawless so far. Everything we've done has made sense algebraically and numerically and things like that. Everything has made sense. So therefore, there's only one thing that went wrong here. If everything here has made sense, everything that we've written, everything that we've done for the last 6 minutes here has made perfect sense, there's one culprit. And that one culprit has to be at the very beginning, our assumption here. We made this assumption, so the only reason we went off the rails on this crazy train, ladies and gentlemen, is because of the fact that we made this assumption at the very beginning. And that assumption led us to a contradiction. So therefore the assumption cannot work. So our logic has been flawless. Our assumption must be false since it led to a contradiction. Therefore, the assumption is false. Therefore, the assumption is false, so square root of 2 is irrational. And there you go. So notice that this proof here is indeed showing that the square root of 2 is irrational, and this is done by contradiction. Probably one of the most beautiful proofs out there. Very simple, very simple in its concept, but amazing in its execution. Okay. Now, again, I'm not going to ask you to memorize this proof, but I really want you to just sit here and just think about the proof for a bit and really try to appreciate it. Okay.